In this video, I want to look at the sum and difference rules for finding antiderivatives. I want to start with a basic fact from Calculus 1. I want to remember that in Calculus 1, we learned how to find the derivative of sums and differences. The derivative of capital F plus capital G is just capital F prime plus capital G prime. And if I think about wanting the derivative of a difference of capital F minus capital G, that's just going to be the difference of the derivatives. So what I now want to do is I want to use this fact to find antiderivative rules. So I'm going to let the antiderivative for little f of x be capital F, plus, of course, any constant that I want to add, so I'm just going to call it C1. And I'm going to let the antiderivative for little g of x be capital G of x, plus any constant that I want to add called C2. Now, what I want to notice is this. If I look at the derivative of capital F of x plus or minus the capital G of x function, I am going to get f prime plus or minus g prime. But now this fact up here says that capital F prime is exactly equal to little f, and this fact here says that capital G prime is equal to little g of x. And so I can use these facts down here to say that the derivative of capital F plus or minus capital G is going to be little f plus or minus little g. And I can then rewrite this derivative fact as an antiderivative fact. The antiderivative of f of x plus g of x is going to be capital F plus capital G plus whatever constant I want to add. And if I want to think about putting in a minus sign between little f and little g, that's just going to put in a minus sign over here. Now, this particular rule that we've just established can be rewritten in just integral sign notation as follows. We can say that the integral of little f plus or minus little g of x with respect to dx can be rewritten as the integral of f of x dx plus or minus, depending upon which one you have here, the integral of little g dx. And what I now want to do is I want to use this formula. This here is referred to as the sum or difference formula for antiderivatives. And let me clean up my handwriting there. So this is referred to as the sum or difference rule for antiderivatives. And what I now want to do is I want to use this particular formula to find some antiderivatives. So let's look at some examples. Our first example. I want to find the antiderivative for x cubed plus the sine of x. Well, the first thing that I'm going to do is I'm going to break the integral up at that plus sign. So we're going to be looking at the antiderivative of x cubed with respect to x, and then the antiderivative for the sine of x with respect to x. And I know how to do both of these. This one here is just add 1 to the exponent, divide by the new exponent. And I can add a constant, but I'm not going to worry about that until the very end. And now I've got to find the antiderivative for this one, and the antiderivative for sine x is actually minus the cosine of x, because the derivative of cosine is minus the sine. So we have this minus sign popping up there. And then, of course, we add a constant of integration at the end of this. And I'm going to clean my answer up and say that this particular thing goes back to x to the fourth minus the cosine of x plus any constant that you want to add. Now, it's important to realize that anytime I have an integral problem done, I can do a check. So I want to actually check my answer. And the check is performed by doing a differentiation of the answer. So I'm going to differentiate x to the fourth over 4 minus the cosine of x. And this will be the derivative of x to the fourth over 4. That would be 4 times x cubed over 4 minus the derivative of that cosine of x. Now, in doing the algebra, those 4's cancel out, and I'm now left with an x cubed minus the derivative of the cosine, which is a minus the sine of x. And of course, minus a minus turns into being a plus. So we have x cubed plus the sine of x, which was our integrand. And that's how I know that I got this particular problem correct. Well, let's look at a second example. So, my second example. Let's look for an antiderivative of, let's say, 5 to the x minus x to the 1/2 dx. So to do this particular problem, again, I'm going to break the antiderivative up at this minus sign. So I'll write this as the integral of 5 to the x dx minus the integral of x to the 1/2 dx. And both of these are integrals that we know how to do. This one here is going to go back to 5 to the x divided by ln 5. And this one is going to go back to x to the, I want to add 1 to that 1/2. And when I do, I'm going to get 3/2. And let me make sure my notation is correct. And then I'm going to divide by that new exponent. And then at the end, I add any constant of integration that I want to add. And I just want to clean up this just a little bit. We have 5 to the x over log 5 minus, when we do an invert and multiply, we're going to get 2/3 times x to the 3/2 plus any constant that I want to add for my constant of integration. Again, I want to do the check. So let's check my answer by differentiating it. When I differentiate 5 to the x over ln 5 minus 2/3 times x to the 3/2 plus that constant, what are we going to get? Well, we're going to get the derivative of 5 to the x over ln 5 minus the derivative, of 2/3 times x to the 3/2 plus the derivative of a constant, which is a 0, and I'm not going to bother to write that down. Now, this derivative is going to be 1 over ln 5 times the derivative of 5 to the x, which is ln 5 times 5 to the x. So those ln 5's cancel each other out. Then we have that minus sign. And this derivative here is going to be 2/3 times x, well, I want the derivative of x to the 3/2. So I bring the exponent down. Then I have an x, and then I'm going to subtract 1 off, which will be a 1/2. And that 2/3 and the 3/2 will cancel. And when I notice all of the arithmetic being done, I'm left with the integrand that I started with. 5 to the x minus x to the 1/2. And since this answer is exactly equal to the integrand that I started with, I know that my work is correct.